Power is a word that has a lot of meaning to us in our everyday lives, just like work and energy do. In physics, power has a specific meaning. Power is the rate at which work is done. Now, we've seen a definition similar to that before. The rate. We've seen rate of change of something in the past. Well, anytime we see that word rate, it means the equation looks a specific way. In this instance, we have P, capital P for power, and that rate tells us that we're going to have a division sign with a time in the denominator. Because this is the rate at which work is done, work is what appears in the numerator. So this is one of our equations for power. I say one of our equations for a reason. If I write out the equation for work, work is the force times the displacement times cosine theta. I can develop another equation for power. Power is force times displacement times cosine theta divided by time. Well, we know that the displacement divided by time can be expressed as the average velocity. So another possible equation for power is that power is the force times the average velocity times the cosine of theta. Now, we really only use this second equation if our object is moving at a constant velocity so that the average velocity is equal to the velocity at which it is traveling. And so often when you see this equation, I will not write the AVG for average. And again, we'll only use it when we're talking about moving at a constant velocity. One last fact about power is its units. If you look at this original equation that I showed here, it would seem as though it has units of joules divided by seconds. Now, we said joules was really something else. We said that joules was a kilogram meters squared per second squared. And then I divide that by seconds, which means I have a kilogram meters squared per second, which has another name. It is otherwise known as a watt. The abbreviation for a watt is a capital W. Let's check out our first problem. This one's talking about a skier with a mass of 70 kilograms being pulled up a slope by a motor-driven cable. We want to know how much work is required to pull him 60 meters up a 30-degree slope at a constant speed of 2 meters per second. And then we also want to know what power a motor must have to perform this task. Part A is a review problem from earlier in this chapter. Really, when it says how much work is required to pull him up this slope, we're asking for how much work does the tension do. It says that he's being pulled by a cable, so tension is the force there that's doing that work. So let's say that here's my skier. We all know that I can't draw very well, and my skier is being pulled up this slope. Drawing a free body diagram, we're going to tilt our axis just as we did in Chapter 4, so that the gravitational force would be at an angle. The normal force would be straight up, and tension would be in the x direction. We'll assume no friction in this case, making our problem a bit easier. Next, just as I commonly do when I have free body diagrams, I'll write some net force equations. Specifically, the one that's going to be the most useful to us is the net force equation for the x direction, which says that the x component for the force of gravity minus the tension force equals mass times the x acceleration. Now, if I look back at my problem, it says that he's being pulled at a constant speed. And so that tells me that my acceleration is 0. So the tension force is equal to the x component of the gravitational force. We know the gravitational force is m times g. To get the x component of that force, x in this case would be opposite from my angle, because if this is a 30-degree angle, that 30-degree angle would appear here on my diagram. So x is the opposite, therefore I would use the sine of 30 degrees. I'm not going to calculate what that is just yet. I'm trying to find the work that's done by this force. We know work is force times displacement times cosine of theta. The force is this tension force. So I'll plug in that equation, mg sine of 30 degrees. The displacement is given to me in the problem. And then I say cosine theta. Well, this theta is not necessarily the same as the 30-degree angle I just plugged in. In this case, theta is the angle between the force and the displacement. In this problem, the force is in the same direction as the displacement, so the angle between them is 0 degrees. Now I can go ahead and plug some numbers in. It says that this gear has a mass of 70 kilograms and is being pulled 60 meters up this incline. So 70 kilograms. G we know is 9.8 meters per second squared. Magnitudes only, no vector symbols. Times the sine of 30 degrees. Times the displacement of 60 meters. And we know that the cosine of 0 degrees is 1, so I will not write that out here. Plugging all of this into my calculator gives me a work of 2.06 times 10 to the 4th joules. That's how much work is done by that force of tension. That's the answer to part A. Part B says, what power must this motor have to perform this task? This is a great example of where it is useful to use either equation. However, if I try to use the first equation, the one that says work divided by time, I'd have to find how much time it takes to go up the slope. Whereas, if I use the equation power is force times velocity times cosine theta, then I don't have to find the time because I'm given all of this information. The force in this equation, in this case, is tension, which we said was mg times the sine of 30 degrees. And I multiply that times the velocity. And once again, the angle with the cosine is 0 degrees. So yet again, I have 70 kilograms times 9.8 meters per second squared times the sine of 30 degrees times the velocity, which is 2 meters per second. Multiplying all of this out, I find that it takes 686 watts to go up that hill. Let's look at another problem that needs power where we're looking for power. This one talks about the electric motor of a model train. It accelerates the train from rest to 0.62 meters per second in 21 milliseconds. We know the mass of the train. We want to find the average power that's developed. This is an example where I would want to use the first equation for power. That equation being that power is the work divided by time. I'd want to use that because I don't have a constant velocity in this case. And having a constant velocity is important to being able to use that second equation. Well, to be able to use this equation, I have to solve for a few things. First, I need to find work. Well, we know work is force times displacement times cosine of theta. But I don't know the force, and I don't know the displacement, so I need to solve for both of those. Force, we know, equals mass times acceleration. Really, that's net force equals mass times acceleration. In this case, the force from the motor is really the only thing that's causing that acceleration, because we're going to assume that there's no friction here. Makes our lives a bit easier. Here's the problem, though. We don't know acceleration, so we have to find acceleration, too. To find acceleration, some vector symbols in there. To find acceleration, we're going to use one-dimensional motion. I know that it goes from rest to 0.62 meters per second, and I know the time that it takes to do that. So the equation that I'm going to choose is the one that doesn't have displacement in it, since I don't know that yet. That's the first equation. V final equals V initial plus acceleration times time. That means acceleration is equal to V final minus V initial divided by time. So V final is 0.62 meters per second. V initial is 0 since it starts from rest. When I plug time in, I have to convert from milliseconds to seconds. So I would plug in 0.021 seconds. I end up getting an acceleration of 29.5 meters per second squared. Then I have to multiply that acceleration times mass. The problem gave me a mass of 875 grams, but I need mass to be in kilograms to get newtons out for the force. So I need to convert that. And it converts into being 0.875 kilograms. 0.875 kilograms times 29.5 meters per second squared gives me 25.8 newtons. Now, I know force, and I can figure out the theta, but I don't know delta x yet. So now I got to do another one-dimensional motion equation to find delta x. The one I'm going to use here is the one that doesn't include that acceleration, simply because if I had screwed something up there, I wouldn't be using my mistake twice. So I'm going to pick the equation that doesn't have that acceleration in it, since I know all of the other information. I know V final is 0.62 meters per second. I know V initial is 0. And I know time is 21 milliseconds, or 0.021 seconds. I get a pretty small displacement when I do that. When I think about the problem, it makes sense. So now I have a force, I have a displacement, I have a theta, so I can now finally calculate the work. So work is force, 25.8 newtons, times displacement, 0.00651 meters, times the cosine of the angle between them, and the angle between force and displacement is 0 degrees. To find the power, I take this work, 0.168 joules, I divide it by the amount of time that it takes, 0.021 seconds, and I end up with 8.01 watts.